Building the Ma'anshan Yangtze River Bridge requires lifting heavy steel segments weighing up to 720 metric tons, more than 200 meters into the air, a task that pushes conventional physics to the breaking point. At these heights, wind and weight create lethal torsional stresses that would buckle standard equipment. To survive, the Zoomlion R20000-720 uses a revolutionary moving counterweight technology to shift its own center of gravity in real time. But how does a machine with a 70-meter reach maintain millisecond control over such massive loads without tipping? The answer is an engineering leap that is rewriting the limits of heavy lifting. The Zoomlion R20000-720, officially rolled out in 2023, is categorized as an ultra-large flat-top tower crane. In the heavy machinery industry, the flat-top architecture is a deliberate engineering choice to allow for easier oversailing in congested airspace, as it removes the traditional cat head apex and complex tie rod assemblies. This crane is defined by its rated lifting moment of 20,000 tonne-meters, a metric that combines its maximum load capacity with its reach. The machine is capable of a maximum lifting capacity of 720 metric tons. While it can be climbed to a total structural height of 400 meters, its maximum jib reach, the horizontal distance it can project a load, is 70 meters. The development of the R20000-720 required a fundamental reconsideration of material science. As machines of this scale increase in size, they often fall victim to the square cube law, where the weight of the crane's own steel consumes its potential payload. To solve this, Zoomlion engineers implemented a lightweight, high-load structural design that reduced the upper weight of the crane by more than 20% compared to previous generations of ultra-heavy cranes. This efficiency is the result of 305 invention patents and 158 distinct innovations integrated into the frame. These innovations include high-tensile steel alloys and precision welding techniques that ensure the mass sections can withstand the compression forces of 720 metric tons without deformation. Central to the operation of the R20000-720 is the ETI Intelligent Control System. In a machine this size, mechanical latency, the delay between an operator's movement and the crane's reaction, can be dangerous. The ETI system provides millisecond-level response times, ensuring the load remains under absolute control. The system must constantly calculate the inertia of the 720 metric ton load. A sudden stop at a 7-meter radius would create a lateral shock load capable of twisting the mast. The ETI system manages these forces by softening movements and providing active dampening. To satisfy the requirements of industry professionals, it is essential to note that all lifting and structural weights are measured strictly in metric tons. The crane is designed to operate in extreme conditions, specifically high-humidity maritime environments and areas prone to high-velocity wind gusts. The R20000-720 is not merely a larger version of a standard crane. It is a digitally integrated lifting platform designed to maintain a 60% increase in lifting performance through its mechanical and software synergy. As we look at these specifications, it raises the question: at what point does the sheer physical mass of a machine begin to dictate the very design of the infrastructure it was built to create? The deployment of the R20000-720 on the Ma'anshan Yangtze River Bridge and the Zhejiang Bridge addresses specific geographic and structural limitations. These bridge projects utilize massive prefabricated steel segments to minimize the time spent on hazardous, high-altitude work. However, these segments often exceed 300 to 400 metric tons, putting them well beyond the capacity of standard tower cranes. When constructing a bridge tower in the middle of a major waterway like the Yangtze, ground-based crawler cranes are often physically impossible to use. The depth of the water and the distance from the shore mean the crane must be mounted directly onto the bridge pylon or a temporary steel platform. Smaller tower cranes lack the lifting moment to reach the center of the pylon with a heavy segment. If the crane cannot reach the required radius, the entire bridge design must be compromised, breaking the towers into smaller, lighter pieces. This significantly increases the number of high-altitude welds and bolts, which introduces more potential points of failure and dramatically extends the construction timeline. Wind resistance is the primary environmental enemy in these projects. At 200 meters elevation, wind speeds are significantly higher and more unpredictable than at ground level. A large bridge segment has a massive surface area, causing it to act as a sail. On a standard crane, the resulting torsional stress, the twisting force on the mast, would be catastrophic. The R20000-720's mast is designed with a wider footprint and specialized bracing to counteract these forces. Furthermore, the industry practice of tandem lifting, using two cranes to move one load, is a high-risk operation. If the two cranes are not perfectly synchronized to the millisecond, the load can shift, causing one crane to take on 80% or 90% of the weight. This shock load often results in the failure of both machines. The R20000-720 provides a singular high-capacity solution that eliminates the need for tandem lifts, simplifying the lifting plan and drastically reducing the risk of a site-wide disaster. This machine turns a high-stakes engineering problem into a controlled assembly process. The defining innovation of the R20000-720 is its revolutionary moving counterweight system. In a conventional tower crane, the counterweight consists of a series of concrete or steel blocks fixed at a permanent position at the rear of the counter jib. This design is inherently flawed for ultra-heavy lifts. When the crane is not carrying a load, the fixed weight makes the structure back-heavy, compressing the rear of the mast. Conversely, when the crane lifts its maximum 720 metric ton load at a long radius, the structure becomes front-heavy, stretching the rear mast components and compressing the front. The R20000-720 bypasses these structural stresses by making the counterweight dynamic. The counterweight blocks are mounted on a rail system and are moved forward or backward along the counter jib by a series of high-torque actuators. As the trolley moves the load outward along the main jib, the counterweight simultaneously moves backward to compensate. This active adjustment ensures that the center of gravity of the entire upper works remains localized over the center of the mast, regardless of the load's position. This moving counterweight technology has resulted in a 60% increase in lifting performance compared to fixed counterweight designs. By maintaining a balanced state, the crane reduces the deflection or bending of the mast. For bridge engineers, this stability is critical. When placing a heavy segment up to 720 metric tons, the bolt holes in the steel must align within tolerances of less than 5 millimeters. A swaying mast makes this level of precision impossible. The ETI Intelligent Control System manages the counterweight movement with millisecond precision. If the counterweight were to move out of sync with the load, it could induce a dangerous oscillation. Sensors at the hook and on the trolley track provide constant data to the ETI system, which calculates the exact position the counterweight needs to be in to maintain equilibrium. This creates a state of constant re-engagement between the machine and the load, resolved through millisecond adjustments. For the operator, the machine feels remarkably stable, allowing for the safe execution of lifts that were previously considered beyond the mechanical limits of tower crane technology. Given the precision required for this counterweight movement, one has to wonder if the future of heavy lifting lies less in the strength of the steel and more in the speed of the software managing the load. Deploying the world's largest tower crane is a massive logistical operation that begins months before the first lift. The R20000-720 cannot be transported as a single unit. It is broken down into hundreds of specialized components. These include the individual mast sections, the long jib segments, the counter jib, and the mechanical hoist units. Each of these components requires heavy load permits and specialized low-loader trailers. Transportation to sites like the Ma'anshan Yangtze River Bridge often involves a combination of road and water transport. Once the components arrive, the assembly process, or rigging, begins. This requires a fleet of smaller assist cranes, often in the 100 to 200 metric ton range, just to establish the foundation and the first several levels of the mast. The base must be anchored with extreme precision, as even a fraction of a degree of tilt at the base would result in several meters of lean at the 400-meter maximum height. The most critical phase of deployment is the climbing process. The R20000-720 uses a hydraulic climbing frame that encircles the mast. This frame uses massive hydraulic rams to lift the entire upper structure, including the jib, counterjib, and cab, high enough to slide a new mast section into place. This process is repeated until the crane reaches its required working elevation. During this phase, the crane is at its most vulnerable to wind and mechanical failure, requiring 24-hour monitoring and perfect weather windows. The financial and engineering stakes of this deployment are immense. A single damaged pin or a misaligned mast section can halt a multi-billion-dollar infrastructure project, resulting in millions of dollars in liquidated damages. However, once the R20000-720 is fully assembled and calibrated, it becomes the centerpiece of the project. It represents the resolution to the industry's most pressing problem: how to build at a scale that exceeds the capacity of our previous tools. The crane is a testament to the fact that in modern engineering, we no longer just lift heavier, we lift smarter through the application of active balancing and intelligent control. As we look toward the next generation of infrastructure, the success of the R20000-720 on the Ma'anshan Yangtze River Bridge and the Zhejiang Bridge sets a new baseline for what is possible. The move toward modular, prefabricated construction is only accelerating, and with it, the demand for even higher lifting moments. Engineers are already analyzing data from the R20000-720's ETI system to refine the next iteration of intelligent controls. The global perspective on these machines is shifting. They are no longer seen just as tools, but as critical infrastructure themselves. The ability to move 720 metric tons with millisecond precision has implications beyond bridge building, potentially influencing heavy industrial assembly in the mining and power sectors. By shortening the fall-off sections of project timelines, where progress usually stalls due to lifting constraints, machines like the R20000-720 are fundamentally changing the economic viability of mega projects. This continuous improvement mindset ensures that the industry remains focused on delivering expectations and exceeding them. The integration of 305 invention patents into a single machine is not just a point of pride for Zoomlion. It is a roadmap for the future of engineering, where the melody of the build, the flow, the pacing, and the precision comes together in a perfect high-load harmony. Looking at the rapid evolution of these ultra-large cranes, it prompts a reflection on whether we are approaching a definitive limit to human-scale construction, or if this is simply the baseline for a new era of industrial ambition. The Zoomlion R20000-720 is more than just a massive collection of steel and hydraulics. It is a monument to what is possible when active intelligence meets 20,000 tonne-meters of raw lifting moment. By combining a 720 metric ton maximum capacity with the millisecond precision of the ETI intelligent control system, this machine provides the definitive resolution to the challenges found on the Yangtze River. The active balance technology doesn't just increase performance by 60%. It proves that in modern engineering, we no longer have to succumb to the weight of our own ambitions. We simply have to lift smarter. Thanks for watching Hard Hat Industries, your source for serious machines doing real work. If you like this, hit like, subscribe, and turn on notifications so you don't miss what's next. Until then, keep your head down and your gear running.